It came in the same plane as the planets around the Sun that was deployed by NASA. Swan R2, officially known as C20 to 25R2, wasn't spotted until a sudden outburst lit it up in September, shocking astronomers who thought the skies were under control. Now, as it speeds past Mars and heads deeper into October, scientists are warning that it could pose a serious risk for 3I Atlas. Could two cosmic wildcards really arrive at once? And if Swan R2 is just the opening act, what terrifying surprises are still hiding in the data? How it escaped detection? With all the technology aimed at the skies, you'd think every comet would be spotted months, even years before it makes a close pass by Earth. That's what makes Swan R2 so unusual. It wasn't tracked. It wasn't predicted, and it wasn't sitting in the databases of Pan-STARRS, Atlas, or the other major sky surveys. It forced its way onto the stage only after an eruption made it bright enough to ignore. Here's how it slipped through. Most surveys are designed to look for faint, slowly moving dots against the background stars. They're excellent at spotting near-Earth asteroids because those are small and steady. Comets, though, are trickier. When they're far from the Sun, they're just dark chunks of rock and ice, too dim for the systems to catch. Swan R2 was one of those faint wanderers coasting along without any noticeable activity. Until September, it was effectively invisible to all but the most powerful telescopes, and even then, it wasn't drawing attention. The outburst changed everything. As sunlight heated the surface, gases trapped beneath the crust suddenly vented, blasting dust into space and creating a visible coma. That coma scattered sunlight efficiently, turning Swan 2 into a glowing smear that popped up in surveys and telescopes almost overnight. What had been an anonymous rock on the edge of detectability became the brightest new object in the region of the sky it occupied. The fact that it avoided detection until that moment is more than just a curiosity. It highlights the limits of even the best monitoring system. Automated telescopes scan huge swaths of the sky every night, but they rely on consistency. Objects that stay faint and then flare suddenly can fall right through the cracks. Swan R2 is a perfect example. Quiet for long enough that no one noticed, then loud enough that the entire astronomical community had to turn and pay attention. In a time when we like to think the sky is mapped and predictable, Swan R2 proved it isn't. It reminds us that new arrivals can still sneak past the watchtowers and appear without warning, rewriting the night sky in a matter of hours. What an outburst really is. When astronomers say a comet has erupted, it doesn't mean fire and explosions the way it does on Earth. What Swan 2 experienced in mid-September was a textbook cometry outburst, and the mechanics behind it are both simple and dramatic. A comet is basically an icy body wrapped in dust. Most of the time, especially when it's far from the Sun, that ice is locked solid. But as the orbit carries it closer in, sunlight begins to seep into cracks and weak spots. At first it's subtle. Ice is warm. Vapor pressure builds. Small jets of gas begin to trickle out. Then comes the breaking point. A sealed pocket of carbon dioxide or methane suddenly ruptures, venting all at once. Dust, ice shards, and gas burst into space, inflating a fuzzy envelope around the comet's core called the coma. That's the glowing halo you see in long exposure images, and it can swell to tens of thousands of kilometers wide for Swan R2. The outburst was strong enough that the comet jumped several magnitudes in brightness. That's not just a subtle increase. It's the difference between being invisible to backyard observers one night and showing up in binoculars the next. The coma reflects sunlight efficiently, and molecules like cyanogen and diatomic carbon fluoresce under ultraviolet light, giving the comet its ghostly green tint. At the same time, solar radiation pressure pushes dust away, forming the long, thin tail that points directly opposite the Sun. What makes outbursts unpredictable is that they're controlled by the comet's internal structure, which no telescope can see in advance. Some comets erupt multiple times, each burst stronger or weaker depending on how much volatile material is left beneath the crust. Others flare once and then fade quickly as if they used up their fuel in a single event. Swan R2 has already shown signs of erratic behavior with brightness spikes that don't follow a neat curve. For scientists, these outbursts are like peeking into a time capsule. The gas and dust being released have been preserved since the solar system formed 4.5 billion years ago. For skywatchers, they're what transformed an anonymous rock into a headline-worthy comet. Swan R2's September eruption was its debut, the moment it stopped being invisible and became something people could chase across the sky. The celestial roadmap. Once Swan R2 made its dramatic entrance, Astronomers quickly mapped its track through the sky. Unlike planets, which move slowly along predictable paths, comets cut across constellations with noticeable speed. If you watch night to night, Swan R2 doesn't stay put. It slides against the background stars, giving the impression of a traveler moving from one landmark to the next. At the end of September, it was already brushing past Mars and Spexer, two bright guides in the southern sky. By October 1st, it made a close pass by Zubanel Ganubi, the brightest star in Libra. For observers, that encounter provided a convenient signpost. Find the star, and the comet was right there beside it, glowing as a faint but distinct smear. The route doesn't stop there. Over the following weeks, Swan R2 shifts eastward into Ophiuchus. On October 13th, it sweeps past Sabi, a bright star that marks the southern side of the constellation. That pairing is especially useful for binoculars because Sabi anchors your view while the comet appears nearby, its coma looking like a soft disk and its tail tapering off into the dark. By mid-October, the comet enters one of the richest parts of the sky. On October 17th, it passes through the region of the Eagle Nebula, home of the famous Pillars of Creation. This is where astrophotographers get their dream shot. A low-power eyepiece or a wide-field camera setup can frame both the comet and the nebula together, giving the impression of an icy traveler cutting across a stellar nursery. Few comets are lucky enough to pass through such dramatic scenery. After that, Swan R2 accelerates. As it nears its closest approach to Earth around October 20th, its apparent motion picks up. You'll be able to notice its shift night by night, sometimes degree by degree, as it races through Serpens and Scutum. Each evening, the comet is in a slightly different place. So, tracking it feels like following a moving target across a cosmic map. This roadmap isn't just astronomy jargon. It's a practical way for people to find the comet night after night as it leaves behind one set of constellations and cuts through the next. Swan R2 is literally drawing a line across the sky, and the landmarks along the way make sure no one loses track of the chase. The observer's guide. Knowing the comet's path is one thing. Actually spotting it with your own eyes is another challenge entirely. Swan R2 sits low after sunset, and that makes the conditions tricky. The glow of twilight can wash it out, and anything along the horizon, buildings, trees, or even distant hills can block the view. To give yourself the best chance, you need a location with a clear, open view to the southwest. Rooftops, fields, or coastlines work far better than city streets surrounded by light and clutter. Timing is everything. If you go outside right at sunset, the sky is still too bright and the comet will be lost in the haze. Wait too long and it's already dipped below the horizon. The sweet spot is roughly 45 minutes after sunset. That's when twilight is fading, but Swan R2 is still hanging just above the skyline. On good nights, you'll have a window of maybe 20 or 30 minutes where conditions are ideal. Your eyes alone might catch a faint smudge under dark skies, but binoculars make all the difference. Even a standard 7x50 or 10nx50 pair will reveal the coma as a rounded glow. And on clearer nights, you'll notice the tail stretching away from the sun. Small telescopes provide more detail, but comets aren't really telescope objects in the same way planets are. They're wide and diffuse, so a broader field of view often gives a better sense of the tail against the stars. For anyone with a camera, Swan R2 is within reach. A DSLR or mirrorless setup on a tripod set for 10 or 15 seconds of exposure can capture the coma and tail, even if your eyes can't. Wide field shots show the comet in context with Mars, Spica, or the Milky Way, while longer lenses bring out the subtle green tint and fine dust structure. Observing Swan 2 is about preparation and patience. Some nights will be clouded out, some will disappoint, but when conditions line up, you'll catch a fragile visitor that hasn't been seen before and won't be seen again. That's the thrill. Stepping outside and knowing you're watching something temporary, a comet burning its path across the sky for just a few short weeks. The science grab for scientists. Swan R2 isn't just a sky show. It's a rare chance to study fresh material that's been locked away since the solar system formed. When the comet erupted in September, it spewed out dust and gases that had been sealed for billions of years. Every telescope trained on it since then has been gathering clues about what it's made of and how it behaves under the stress of sunlight. Spectroscopy is one of the main tools in play. By spreading the comet's light into a spectrum, astronomers can identify chemical fingerprints in the coma. Water vapor is a standard find, but Swan R2 has already shown emissions from carbon-based compounds that fluoresce green under ultraviolet light. These molecules, cyanogen and diatomic carbon, are simple by chemistry standards but important in planetary science. They hint at what the early solar system was made of and how those building blocks might have seeded young planets with ingredients for life. Dust analysis is another focus. The tail isn't just decoration. It's a trail of data. Its shape and spread reveal how particles are being lifted off the nucleus. Fine dust creates wide, diffuse fans, while heavier grains trace straighter, narrower paths. Early images of SWAN R2 suggest it's releasing a mix, which could mean its crust is uneven with patches of different density and strength. Even the timing of its outbursts matters. Most comets follow predictable light curves as they warm up. SWAN R2 has been anything but predictable. It brightened suddenly, calmed down, then surged again. That pattern tells astronomers the nucleus isn't uniform. Instead, it's layered with volatile pockets that erupt at different moments, a bit like hidden vents going off one by one. Mapping those changes helps researchers refine models of comet interior, which remain one of the biggest mysteries in planetary science. The value here is immediate. SWAN R2 arrived without warning, but it's giving scientists a chance to test theories in real time. Every spectrum, every brightness spike, every tail shift adds to our understanding of how comets behave and, by extension, how the solar system evolved. For researchers, this comet is less an intruder than a time capsule cracked open at just the right moment. The breakup risk: comets can dazzle, but they can also vanish without warning. SWAN R2 may look like a solid glowing object in photographs, but up close it's fragile. The nucleus is more like a loosely packed snowball than a rock, held together by weak gravity and a thin crust of dust. Every jet of gas that bursts from its surface weakens that structure a little more. If the cracks spread too far or too many vents open at once, the whole nucleus can fragment. That risk hangs over SWAN R2 every night we track it. There's precedent for this. In 2013, Comet YS was expected to become one of the brightest comets in living memory. Instead, as it grazed the sun, the nucleus fell apart, leaving only a fading cloud of dust. Back in 1994, Comet Shoemaker-Levy 9 broke into more than 20 pieces before slamming into Jupiter, producing dark impact scars that telescopes could see for weeks. Even less famous comets, like Comet Linear in 2000, have surprised observers by disintegrating long before they reached peak visibility. These examples show how quickly a promising comet can turn into nothing. SWAN 2 has already shown hints of instability. Its sudden outbursts suggest it's venting violently, not evenly. That kind of activity can be a warning sign of fractures spreading under the surface. If it does split, the view will change almost overnight. Instead of a compact coma with a narrow tail, you'd see a broader, fuzzier glow as fragments spread out and shed dust on their own. For astrophotographers, that would still make for dramatic images, but casual observers might find the comet fading faster than expected. If it holds together, the payoff could be spectacular, especially around its closest approach to Earth on October 20th. The uncertainty is part of what makes comets fascinating. They're not like planets. Steady and predictable, they're fragile travelers. Each pass near the sun, a test of survival. SWAN R2 could blaze for weeks, or it could unravel tomorrow. That tension between beauty and fragility is what keeps astronomers and skywatchers glued to it night after night. Comets as human omens. For most of human history, comets weren't studied. They were feared. A sudden glowing streak across the night sky was treated as a sign that something big was about to happen. Ancient Chinese dynasties kept detailed comet records going back thousands of years, linking their appearances to political upheaval or disasters on Earth. In medieval Europe, comets were painted in manuscripts as fiery swords, symbols of punishment or war. One of the most famous examples is Hall's Comet in 1066, stitched into the Bayeux Tapestry as an omen that foreshadowed the Norman conquest of England. That sense of unease lasted well into modern time. When Hal returned in 1910, Earth passed through its tail. Scientists explained it was harmless, but newspapers printed sensational headlines claiming the atmosphere would fill with poisonous gas. Sales of gas masks and anti-comet pills spiked, and people sealed their windows in panic. Nothing happened, of course, but it showed how easily comets could stir fear. Even in the age of telescopes and newspapers, not every comet inspired dread. Some were sources of wonder. Hale-Bopp in 1997 was so bright that millions of people around the world saw it without any equipment, a spectacle that lasted for months. For many, it was their first real introduction to astronomy. But even then, the old pattern resurfaced. The Heaven's Gate cult convinced themselves that a spacecraft was following the comet, leading to a mass suicide in California. That tragic event was a reminder of how comets, despite all our science, still have the power to fuel myths and extreme. Swan R2 doesn't carry the same level of cultural weight yet, but its sudden appearance has already set off smaller ripple online. It's being nicknamed the Ghost Light or the Green Visitor. Some users speculate about hidden meaning or connected to world events, echoing the same instinct that led ancient scribes to treat comets as signs. The difference today is that every phone can capture and share an image. So awe and superstition spread at the same speed. Comets may no longer rule calendars or coronations, but they still tap into that deep human reaction. Something unexpected blazing across the sky must mean something. The 2025 digital spectacle. One of the biggest differences between Swan R2 and the great comets of the past is how we're experiencing it. In 2025, a comet doesn't just live in the sky, it lives online. The moment Swan R2 erupted, images started flooding social media. Amateur astronomers in Australia and Chile posted long exposures within hours, and those photos were being shared globally before most people even knew the comet existed. That instant access changes everything. In the past, you might have had to wait for a newspaper or a magazine to publish a single grainy photo. Now someone in Cape Town can upload a shot of Swan R2 brushing past Mars, and a teenager in Canada can see it seconds later, even though the comet isn't visible from their horizon yet. Every clear night adds a fresh batch of photos, time-lapses, and live stream. TikTok videos explain how to find it. YouTube channels post real-time feeds of the comet sliding across constellations. For many, the first sight of Swan R2 comes not through an eyepiece, but through a phone screen. Astrophotography has become part of the spectacle. Cameras that used to cost a fortune are now within reach of hobbyists, and software makes stacking and processing images simple. As a result, ordinary people are capturing Swan R2 with astonishing clarity. Some wide-field shots frame the comet alongside the Milky Way, while longer exposures reveal fine dust structures in the tail. These images are collected, compared, and reposted around the world, turning the comet into both a scientific target and a piece of digital art. What this creates is a kind of global skywatch. Even people who will never point binoculars at the horizon feel part of the event because they're seeing it unfold on their feeds in real time. Swan R2 isn't just a faint glow drifting across Libra or Ophiuchus. It's a trending subject, a shared experience stitched together from thousands of perspectives, each one reminding us that a rare celestial visitor is lighting up the sky and the whole world is watching together. That's it for today. What are your thoughts on Swan R2? Let us know in the comments down below. Don't forget to like and subscribe for more quality content.